So we are now in chapter 3, and there's the slides. Just do your usual. There's some pretty decent graphics. Sometimes it's hard to get the best graphic, but that kind of summarizes a lot of the things we're going to talk about here. Also, in terms of staying organized, the notes for this lecture and the lecture after the problem-solving one that we do, so we're going to take a look at practice unit conversion, is mainly qualitative. So if you want to set up the headings or just write down the text or print the slides so you have them there and add notes, that's fine. Well, we're just going to be going through, I think I can step out from behind here, some examples. Now, this chapter is an extraordinarily important chapter because it's talking about the air we breathe on a daily basis. So this is ground level air pollution. And I'm only really sketching some of the highlights and maybe putting it into a slightly different context than the book does. And so we're being very selective with these lessons. Really, I'm going to try to keep it to 2 lessons for the chapter, and then the one problem-solving session where we do different kinds of unit conversions. But I'm going to get to that later. So that's fine. And then when you look at the homework, there's some additional things like looking at certain sections of the book selectively, and then also a little bit of background history, and this is where we're going to start, from about the Clean Air Act. The book, as I recall, especially in this chapter, does not have much on the Clean Air Act, the CAA, from 1970. And this is the federal law. That's what an act is. It's a law passed by Congress that governs air quality. And then states will then take those standards and adapt them to the circumstances that they have. So the Clean Air Act, the CAA, is something you want to have a working knowledge of. And I'm using that as a bit of a framework here in addition to what the book has. But the book, as usual, does a tremendous job. Okay, so let's go ahead and get started. And the first thing, I don't have anything to add for, under letter A, essentials from the Clean Air Act. It gives you a definition of pollutants. I'm not going to write that definition on the whiteboard. That's a waste of time. So any substance or matter that enters the air, including physical, chemical, biological, or radioactive substances. So that's what a pollutant is. And a criteria pollutant, that's an important distinction, is that those are the ones that are measured more frequently and have a certain concentration or a level that's set to protect public health. And different states may have different standards, different countries certainly have different standards, but that's what a criterion pollutant is. And oftentimes I define pollution, it's not a great definition, but it's the wrong stuff in the wrong place in the wrong amount. Something that might be a pollutant in one location, in another location, might not be a pollutant. A perfect example of that is ozone. Ozone is not a pollutant in the stratosphere, it's in fact necessary in the stratosphere. Ground level ozone, however, is a pollutant that we have to think about because it's where we breathe it. So sometimes it can be the same molecule, it depends on where it is and in what amount. As obvious as that might sound, let's just keep that in mind. Okay, so what I'm just doing here is, where am I going? I have to look at my notes and these because I don't have the slides in front of me. So, giving you some examples of primary and secondary pollutants. Okay, let's just go there with those. And I've just got several examples. And so this is under 2A, primary pollutants. And primary pollutants are things that are emitted directly into the atmosphere, I guess more specifically the troposphere. So this is under 2A. How about we use the symbol for primary pollutants? And I put these into a couple of different categories. And I think the book does this too, I don't really remember, but I think it's helpful because it's helpful for things we'll talk about later in this course. Partially oxidized pollutants. Carbon monoxide. Carbon dioxide is a completely oxidized pollutant. And I think we might have done this before. Carbon monoxide has a triple covalent bond in it. And just so you have this in your notes, CO2 is not partially oxidized, it's completely oxidized. That's as far as carbon can go. CO2, there is no such thing as CO3 as a molecule. CO3 with a -2 charge is a carbonate anion, but we haven't talked about that yet. We've also talked a little bit about nitrogen oxides, NO and NO2, and both of those we often refer to oxides of nitrogen collectively as NOx. In this case, these are free radicals, which we've talked about before. Another example of a partially oxidized primary pollutant, again, these are ones that are emitted directly into the atmosphere. They don't have another reaction that makes them a pollutant, is sulfur dioxide. And oxides of sulfur are collectively called SOx, NOx and SOx. Fine. And those are called partially oxidized primary pollutants. Then we have examples of what are called reduced pollutants. You can put your notes top to bottom. And we are going to do a little bit of redox chemistry. We've done a little bit so far, but not much. And something that's reduced is sort of the opposite of the NOx. These are oxidized forms of nitrogen. This is a reduced form of nitrogen, and that's called ammonia. If you want to write that down, it's ammonia. The reduced form of sulfur is dihydrogen sulfide. If you want to write that chemical name down, dihydrogen sulfide. The SO2 and the H2S, if you've ever smelled rotten eggs, if you will, coming off of a power plant, a fossil fuel burning power plant, it's likely because of the sulfur content of the coal or other aspect of the fossil fuels. Methane is the reduced form of carbon. Now, if you have organic chemistry, methane is CH4, ethane is C2H6, propane is C3H8, butane is C4H10. So this is the simplest version, and we can extend that out into other hydrocarbons as well. And the last one is, it's a category, it's not a specific molecule, but it's a really good acronym. So it's not vanadium, oxygen, carbon. That wouldn't make any sense. This stands for, you might already know this, volatile organic compounds. The word volatile here doesn't mean like it's going to explode. That's kind of what it might connote, is that this is a molecule that would explode or catch fire really easily. Sometimes that is the case, but the word volatile means, in this context, is that it turns into a gas easily. So say you have a container of gasoline, and you just let it sit there, and you'll notice it turns into a gas pretty easily because you're smelling it. You can even smell it at the gas station, because it goes from a liquid to a gas very easily, which in terms of physical properties, these tend to have very low boiling points. I didn't know this before I taught the course. Volatile organic compounds are typically in this range of boiling point. 260 degrees Celsius doesn't sound like a low boiling point to me. Remember, the boiling point of water is 100. So I wasn't too sure about that one, but that's where the sort of the range where it falls into. Okay. So those are those are the primary pollutants. Let's see if I can fit this in here. So this is 2B. Secondary pollutants, so things that are, well, they have to be produced, okay? And some examples there. Ozone, as I mentioned before, ozone is not a pollutant in the stratosphere. It most certainly is a pollutant in the lower levels of the troposphere. So we call that ground level ozone. Other things that are secondary, HNO3, H2SO4, which you might remember from general chemistry. That's nitric acid and sulfuric acid. So these are collectively called acidic precipitation. So I read out the whole word, acidic precipitation. Fine. And then sulfur trioxide and nitrogen trioxide, those are the completely oxidized forms of nitrogen, sulfur, well, I was about to say respectively, but I guess reverse respectively. But those are secondary pollutants. And these are completely oxidized versions of what we showed you before for the particles. And then, let me see what else I have for you here. On the slides, yeah, okay. This is kind of an obvious comment here. Is the atmosphere, so the troposphere, tends to be what's considered an oxidizing environment. Well, yes, because there's a lot of oxygen down on the ground level, about 20% of the air you're breathing. So a lot of oxidation reactions take place in the troposphere. It's kind of a duh comment. That will not be a duh comment when we come to water, where, especially we're talking about an area where the water doesn't move very much, like a pond or a lake. It'll be an oxidizing environment towards the top of the pond or the lake, but as you go in depth, it'll switch from an oxidizing to a reducing environment because of the levels of oxygen. For our purposes here, it's an oxidizing environment primarily, but I don't have anything else to add on that with the graphic. And in fact, let me see what I have here in terms of this first lesson is, yeah, the other thing, I'll put it on here, I'm sorry, I'm kind of stumbling a little bit because I'm just really sketching the overview here. The book doesn't talk a ton about these, and I'm not going to add anything to this, is particulate matter. PM is something to pay attention to. And particulate matter is just that. It's a particle. It's not as small as a molecule, but it can go airborne, and it's defined on how big the particle is. The one we want to talk the most about in this course, because it's the most dangerous, and this graphic really does it. I forget where I got this, but it's a good graphic. So you've probably heard about some kinds of pollution, like if you've ever worked in construction, or you go near a construction site and you breathe in dust or you're just around it, well, that's particulate matter too, and that can cause a lot of problems with your health if it lodges in your lungs. And then you've probably heard about things like asbestos, and that can be particulate matter, and it causes all kinds of health issues there. But the one you'll hear a lot about is PM 2.5. So that's particulate matter that has a size of about 2.5 microns, which is the same thing as a micrometer. So 2.5 micrometers, and we're going to learn more about micro, or relearn about that later. Okay, this is probably going to be pretty close to the end of the first lesson. The units for air quality standards. I'm going to set this up. I don't think I'm going to set it up now. So the thing we want to do with the next chunk, and what's coming up here, I think is one of the most important parts of this chapter, is what units are used to measure different criteria of pollutants in the air. And the thing I like about units is you choose the unit that makes the most sense for the pollutant and for the circumstance. And what we want to do is be fluid about converting between different levels of units here. So the units I have under letter B, so that this is not, sorry, not great note-taking today. I'm not going to rewrite those. Parts per million, parts per billion, parts per trillion. Fine. Those we're going to use micrograms per cubic meter, and then also a common unit from Gen Chem, molarity. So I'm going to set this up next lesson, but the main idea is there's a few things we need to be able to juggle when we do these problems. First is the definition of the unit itself. What is a part per million? What is a part per billion? The other units I think are pretty straightforward. Molarity is moles per liter, and then micrograms per cubic meter is pretty straightforward. But to convert these, there's going to be, well, a few things we're going to need to be able to do, depending on it. We're going to be able to use the Greek prefixes. Micro, milli, the Greek prefixes. We'll also need to remember the ideal gas law, PV equals nRT. We'll also need to be able to remember the periodic table. That's how you convert between grams and moles, so make sure you have your periodic table ready. And let's see, what else? I think that's it. So there's a lot of pieces of the puzzle, and if you think you know what you're doing, you can use the examples in the book and work out the problems on your own. I'm gonna work through them probably in a little bit, not haphazard fashion, but we'll just see how it goes. Okay, so the problem solving session is next.